right. Let's get started. Lecture 27. I think we only have 41 lectures, so I mean we're like in this last third of the semester. Like it's one of those things like, did it go fast or did it go slow? So, all right. A couple of announcements. Attendance grades are up to date on Blackboard. Homework 6.1 is being graded. Homework 6.2 was due today, and I know that one was kind of a long assignment. That was, and I was saying this before class, I think the longest homework in the class, period. So after this, it gets a lot shorter. Homework 6.3 and 6.4 are going to be due Wednesday. Now, if you recall, homework 6.3 is just the install mass stand and upload a screenshot indicating that it's running on your computer. That's all that is, okay? I will say that if you haven't already installed Masthand, please try and do it soon. I mean, obviously for the homework, but if you're encountering any installation issues, let me know. For the folks running Apple laptops, there's a link on Blackboard that might help you install it in case you get any security issues and whatnot. For Windows machines, shouldn't be too big of a deal. Homework 6.4 is due Wednesday. I'm not going to accept any homework that's late for 6.4 because I'm going to post the solution right at 11 because you have a celebration on Friday and I want you to have the solution available to you for studying. So speaking of, we have exam review on Wednesday, so come prepared for questions for the upcoming celebration on Friday, okay? Any questions? All right, so Wednesday's exam review, Friday is the exam, okay? Sound good? Okay, so today we're going to finish our discussion on deflections, and what we're going to do is we're going to kind of generalize our understanding of virtual work a little bit. Let's make sure that we're just clear on what we've been doing so far. So for beam deflections, we've been looking at computing the deflection of a beam as the sum of these, okay? The sum of little m big M over EI, the sum of these integrals. So we take a real moment function, a virtual moment function, divided by EI, and we integrate that. If we only need a single moment function, we just integrate this. More often than not, in real problems, we have to actually sum up a number of integrals. And don't forget, we have our conversion factors to consider as well. I want to generalize the method of virtual work a little bit, and I've removed a lot of the subscripts from this just to get to the heart of what we're talking about here. So far, we've only been considering, so if we're looking at beams, we've only been considering the bending effects of computing deflections, okay? But in general, for a general structural system, so if I give you some structural system, and I don't tell you anything at all about what it looks like, I don't tell you anything at all about what's going on, then as an analyst, you should consider that potentially all this stuff could happen, okay? Like if we're talking about a truss, we have axial deformation, but there's also for flexural structures, we have flexural deformation. If we were twisting the structure, we might have torsional deformation. So this might, some of this notation might jog some of your memories from Engineering 216, Mechanics of Deformable Bodies, right? Remember TL over GJ to get the angle of twist. Shear deformations, I'm going to talk a little bit about that later. I'm not expecting you all to do anything related to shear deformations in this course, but I just want to mention it. And then there's also the potential for thermal elongation. So for example, you take a truss and you heat it up. We're not going to do anything with it, but there's nothing really special about it because all it is just basic mechanics that you did last semester. What I would say is that as the analyst, when we're computing deflections, we really only consider the terms that are relevant. So for example, if we have a truss and we're not worried about thermal loads or anything, we're only considering the axial deformation terms and we're taking all these other terms to be zero. But I posit to you that it's possible that a structure could deform in more than one way, okay? And considering all of these, we might get different answers. And we're going to talk about when to consider certain things a little later. So for frames, okay? So for frames, I propose that for frames, we could consider, if all we're talking about is 2D frames, and all we're talking about is mechanical effects, then I propose that we would have three components to consider: axial deformations, flexural deformations, and shear deformations. Okay? Now I'm not going to worry about shear deformations with you all right now. We'll talk about that a little bit later. So what we're only going to consider for our purposes is axial deformation and flexural deformation. Okay? Now the process isn't going to change. Okay? We're still only going to perform two analyses: the real structure and then the virtual structure, where we remove all the loads and we only place a single load at the point of interest with a magnitude of 1 in the assumed direction. Okay? What I propose to you, and I think the only way to really show you is to actually do an example, is that, so for frames, just for now, we'll talk about shear deformations later, but if you're only considering flexure and axial, then I propose that for most frames, you can neglect the axial deformations. And the best way of explaining that is to do an example. So we're going to look at this structure, okay, and we're going to compute the deflection at point A, and we're going to, so a lot of the problem is going to be the same. We're doing a real structure and a virtual structure, but we're going to compute the deflection sort of considering two things. The first is we're only going to consider flexural deformations, and then the second is we're going to consider both axial and flexural deformations. And just to be clear what I'm talking about, what I'm saying is that if I have flexural deformations, I'm talking about the member deforming in a bending type fashion. I'm talking about it bending. Whereas if I'm talking about axial deformations, I'm talking about the element stretching or compressing along its axis. Okay? And I propose you're going to get deformations from both modes, but one of them you can kind of ignore, and you'll see what I mean. Okay? Now I've done a little bit of work for you already, which is a little atypical, but I want to get our discussion on the way for shear deformations. I kind of want to talk about that for a little bit. So what I've got here, and I'm going to kind of do this problem side by side, is I've got the real structure and I've got the virtual structure. Okay? Now what I've done here is here's the real structure, the original loads that are present, and I went ahead and did the reactions for you. I have to believe that by now y'all are good with that. We don't need to go through that. I think we're pretty good on computing support reactions. And same for the virtual structure. What I did for the virtual structure is I removed all the loads and I placed a single unit load going downward. I'm assuming that on this structure, point A goes down, so I placed a downward load right here. And say, so no loads except for a downward load right here, and I've got the reactions here. Now, what I'm going to do ultimately for this problem, let me get this out of the way. What I'm ultimately going to do is I'm going to compute the deflection as the sum of these, and so we'll call this delta axial plus this, and we'll call this delta flexural. Okay, so I propose that the deflection at A is going to be a function of both of these terms. Okay, but when we actually see the numbers, we're going to see that we can probably neglect this one. Okay, so let's just see what happens. Okay, now what I'm going to do is I'm going to analyze both structures. I'm going to keep the real structure over here on the left and the virtual structure over here on the right. But I'm going to do something a little different for this example, but I kind of have a point I want to make with it. I'm going to analyze the virtual structure first. Okay? There's no rule that says I have to do the real structure first. It doesn't really matter. But for this particular example, there's kind of a reason why. I'm not saying that you should analyze the virtual structure first or the real structure first. You'll see the point I'm about to make here in a bit. Now, the only other thing I want to mention before we actually start getting into the example are my coordinate systems. So what I'm going to do for this example is I'm actually going to use two coordinate systems. So I'm going to have one coordinate system that starts here and goes up, so we'll call that x1. And so I'll probably end up cutting a section, section 1, 1 like this. So if I do that on the real structure, I need to do it on the virtual structure. So I'm going to have, an x-axis that goes like this. So we'll cut a section like that. And then I'm going to have another axis that starts at the fixed support sorry, let me redo that. That starts at the fixed support and goes like that. So we'll call that X2. So when I cut a section like this, cut like section 2, I'm going to cut a section and look to the right is essentially what I'm saying. All right. So I'm going to cut a section and look down, and then cut a section, look to the right. Cut a section, look down, cut a section, look to the right. Okay? Is everybody with me on this? So far, so good? Okay. All right. So like I said, I'm going to do the virtual structure first. Okay? Does everybody have all this? I got all this? Okay. I'm going to cut a section, and well, I'm going to start looking at this virtual structure. So let me draw this down. Okay? So let's start off with section 1-1, and I'm going to look downward. Okay, so let me scroll up a little bit so we can kind of see what's going on. So I'm cutting a section and I'm looking downward. Okay, so I've got okay, so cutting a section looking downward, this is what I've got going on. All right, so cut my section. Okay, so whenever you cut a section through an arbitrary point in a structure, you have how many, at most, how many unknowns? If I just cut a section through a random arbitrary point in a structure, how many unknowns do I have? 3, right? An unknown force in the x direction, unknown force in the y direction, unknown moment. Everybody with me on that? So if I look at this, that means I have an unknown force, let's say in the x direction, unknown force in the y direction, unknown moment, right? With me so far? So we'll call this, let's do it, I don't know, like that. Okay? So if I sum forces in the x direction, that's going to be here. Let's label these a little bit. Let's label this. So let's call this right here, let's call that the shear. Let's call that the axial force, and let's call that the moment. Okay? So if I sum forces in the x direction, what's that going to tell me about V? 0, right? So V equals 0. Okay? So maybe we'll use a lowercase v. V equals 0. Maybe what I should do, maybe I should label this like little f and label this little m since I'm doing the virtual structure. Maybe I should be consistent there. Okay. So if I sum forces in the y direction, what is my axial force going to be? What's the force in the y direction going to be? If this is 1 down, what's this going to be? 1 going up, right? So we'll say 1 going up, or more specifically, 1 in tension. Is that a fair statement? Okay. Now, if I sum moments, what's my little m? What's this little m going to be?
0.
It's 0, right? Okay. So if I were to write this maybe a little bit more formally, maybe what I'll do is I'll say F, and we'll call it member AB, is 1, assuming tension is positive, and that's from x equals 0 to x equals 10, and MAB is 0, and that's going to be valid from 0 to 10. Does that make sense, what I'm doing right here? Now, why am I not writing the V? Like, why do I not care about the V? Because I'm not going to use it, okay? For this problem, I'm not going to use the V. I'm only going to use the little f and the little m, okay? I mean, I could use the V later, but right now I don't really care. Make sense? It wouldn't matter anyways because it's 0. Okay. So far, so good? Okay. So now what I'm going to do is this. So I'm going to now look at the same problem over here. All right, so now I'm going to look at the real structure, and I'm going to cut a section and look down. So let's draw that out, okay? So I've got, here's my structure. All right, so I've got 20 kips, 10 kips. Here's where I've cut the section. This dimension is x1, right? That's x. Okay, so that's my x-axis, or my unknown. And then I'm going to have the same unknown quantities to consider. Maybe we'll use capital letters for this. So we're going to have, you know, a shear. Now notice how I'm drawing. I'm going to draw everything in the same direction. So a right and a right. We'll draw the axial force in the same direction. F and do that. Okay. Now let's be a little bit more streamlined about this. I only care about the F and the M. So let's see if somebody can tell me what's going on here. What about the F? Okay. What is FAB going to be over here? 10, right? Because I've got 10 down and 10 up. So this is going to be 10, and it's going to be valid from 0 to 10. Now, watch this. Watch what I do here. What's MAB? Here's going to be my answer. Who cares? Why did I write that? Because the little one's 0, right? Who cares, right? Because what I'm ultimately going to do, let's expand this a little bit. So what I'm going to do is I'm going to have a little FAB, big FAB, plus little FBC. Right? That's going to be my delta axial, right? Right here. This is my axial deformation, but I'm also going to have the same thing over here. I'm going to have an integral from 0 to 10 of this plus an integral from 0 to 20 of this. But what did we just discover? This is 0, right? Because if the little m is 0, I really don't care what this is, because this whole integral is going to go to 0. So the point I was making when I said I was going to do the virtual one first is that if you're looking at these structures and you get a 0 term over here, you really don't need to go through the effort of deriving the associated expression over here, because when you integrate it, it's going to be 0, right? Does that make sense? That was the point I wanted to make with this. That was kind of why I did the virtual structure first. Okay? Make sense? So you could argue that in some cases it's sometimes advantageous to do the virtual one first, because you have a better chance of having a 0 force section on a virtual structure since there's a lot less loads. So just worth mentioning. Okay. So what I'm going to do now is now I'm going to look at section 2.2. Now, let me scroll up a little bit to make sure we're all on the same page. So now what I'm going to do is cut a section here, and I'm looking to the right. So with both sections, I'm going to cut a section and look to the right. So if I cut a section on the virtual structure and look to the right, it's going to look something like this. So let me give myself a little bit more room here. That's probably good. So if I look to the right, what I've got is let's see. So I've got, here's the beam, here's my support reaction, and then I've got my reactions over here, which This one right here is 1. This one is 20 or 20 feet. This distance here, x2. Okay, and then let's put the unknowns, and we can draw them all, but I'm only going to care about 2 of them. So I'm going to have a V, F, and N. And I'm drawing those in their positive sign convention. When you cut a section and look to the right, upward shears, clockwise moments, and then the axial forces in tension. Okay? Now if I look at this free body diagram, what is F? What is F going to be? 0. There are no forces going to the left or right, so that's 0. Okay? So, and that's going to be valid from 0 to 20. Is everybody seeing how I'm coming up with 0 and 20? Because that's how long the element is, right? The beam, the flexural element right here is from 0 to 20. Okay? So, what am I going to say then over here? If I know that this is 0, I'm going to say big FBC is, I'm going to say who cares what big FBC is, because what I'm getting at is that this term right here, that's going to be 0, right? Because this whole fraction is going to be 0 because that's 0. Okay? Now for the moment, we are going to have a moment here, so what I'll do is I'll sum moments at the cut. All right, so we'll sum moments at the cut. Okay, so we're summing moments at the cut. Do I have to consider any of this stuff in blue? I don't have to worry about any of that. I have 1 times x2, and I have 20 going this way. So I have 1 times x2. Is everybody following along with me on that? Then 20 going like that. And then I've got the m. Here, let me write it like this. I've got the m going like that. Do a little better on that. So MBC plus 20 is x2. So therefore, MBC is x2 minus 20. Okay? And that's going to be valid from 0 to 20. And maybe what I should be clear about, maybe I should write it like this. Maybe I'll do this. Maybe I'll say from x2 is 0 to x2 is 20. If you want to write it like that. Okay. Everybody with me on that? So now what we'll do is we'll do the same thing over here on the right or on the left. The same thing that we did on the right, we're going to do it on the left. Okay. So now we've got a little bit of work cut out for us because we got to draw all this out. So let's see, let's get our reactions down. So we got a lot going on here. We've got a 70 kip reaction like that, a 600 foot kip reaction like that, and we have a 20 kip reaction like that. Then And so there's where we cut the section. This was 3 kips per foot. And let's just make sure everybody's awake. What's this distance right here?
X.
There we go, X. Or X2, because we're using that coordinate system. But yes, it's X. Okay? And so what I'm going to do is I'm going to identify my unknowns. Same pattern over here as over here. So we're going to have a unknown axial force. So we'll call that big F. An unknown shear. We'll call that V, big V, and then big M for our unknown moment. Now, again, what is FBC over here? I mean, we can look at it, but really, who cares? Nobody cares, right? Because ultimately that big FBC is going to be multiplied by 0, and that whole term is going to go away. All right. Now, the M, though, that's a little different. We're going to have to do a little bit of work on the M. So we're going to sum moments at the cut. Okay, so we're going to sum moments at the cut. All right. So we don't have to deal with any of this. Should we do something with this distributed load? Maybe we'll take that and collapse it into a single point load. And how much is that point load? 3x, yeah, 3x. And then the distance from here is
x2 over 2.
There we go. All right. So summing moments at the cut. So it's the same distance either way. We don't have to worry about any of these, but we do have to worry about the M. So we've got the M over here. So MBC. We've got 3x times x over 2. And then we have 600. And that's going to be resisted by what? Does the 20 kips generate moment? What about, we already counted for that, what about that? And the moment arm is x2. So MBC plus 600 plus, what is that going to be? It's going to be 1.5, what is that, x squared? Here, I'll move that over a little bit. Right, so therefore I can solve for MBC pretty easily and say that MBC is going to be 700 minus 1.5 x squared minus 600.
Is it 70 or 700?
It's 70. Why did I? Yeah, you're right. That's 70. Got ahead of myself with the hundreds. And this is from x2 is 0 to x2 is 20. All right. So far, so good? Okay. I'll give everybody a sec to catch up with me. Scroll down a bit. Okay. So the way I'll handle the method of virtual work, so you see what I've got here going up on the board. What I'm going to do is I'm going to handle, I'll do the flexural first, then the axial. So let's go ahead and evaluate this, okay? And you can see the two that I'm really going to have to worry about are these two right here. Okay? So what I'm going to do is I'm going to handle delta flexural. And it's going to be the sum of the integrals of the little m big M over EI. Okay? Which is going to be what? Okay, so we're going to have, so let's not forget our 1728 over EI. So for this structure, every member has the same EI, so that's going to make that part a little easier. And we're going to integrate from 0 to 10 little MAB, big MAB, dx. But remember, we already figured out that that one was going to go to 0. So really all we're going to have to worry about is the integral from 0 to 20. Maybe I should put dx1. Little MBC, big MBC, dx2. So all I've got to worry about is 1728 over EI times the integral from 0 to 20 of, okay, and I can see it right here on the top of the screen. So little m is x minus 20. Big M is 70x minus 1.5x squared minus 600 dx. And I'll put this up here just so that everybody has it. For this problem, we were given E was 30,000 KSI. We were given I was 800 inches to the fourth, and A is 4 square inches. So just so we have that, you know, handy. Okay? Now, this right here at this point is just a calculus problem. I've got to believe that you all have multiple means by which to do that. If you want, we can break out the Wolfram Alpha, because I know engineering students love to use Wolfram Alpha for calculus homework. You're like shaking your head like you really brought up Wolfram Alpha. Yeah, I brought up Wolfram Alpha. All right, so, but I believe that you all can chug this out. When you chug it out, you're going to get an answer of plus 3.36 inches. Okay, so I propose that delta flexural is 3.36 inches going down. Okay, why am I saying it's going down? Because I put the virtual load going downward and I got a positive answer. Okay, everybody with me on that? So if you're okay with that, for delta axial, this is sort of like what we did with truss land. All we're doing is we're summing up. So if we want to get technical, okay, what we really should be considering is that we're summing up the integrals. But for both members, the forces were constant. So really what we're just summing is those fractions, which is little f, big F, L over EA plus little f, big F, L over EA. But like with last time, we have one of these which is going to 0. This one's going to 0 because we got one of the virtual forces was 0. So we know we don't need to worry about that term. So we plug and chug, so we'll just worry about this fraction right here. So we got little f of 1. We got big F of 10 kips. We got the length. What is the length of member AB? Sure we're all paying attention. $10 feet, right? So we're just talking about this column element right here. We're just talking about this element right here. So that element is 10 feet long. All right. We've got, bless you. So we've got a 30,000 KSI here, and a 4 square inch area here. Does anybody see a problem? Anybody see it? Well, if we just chug this out, what's our answer going to be in? Well, follow with me on the bottom. KSI in inches squared. What are the units of the denominator? If we have KSI times square inches. Kips. And what are the units up top? Kips times feet. So if we chug this out, we're going to get a deflection in feet, right? Do we like deflections in feet? More often than not, the answer is no. Because if anything, we want to compare to this. So what I'm going to do is do what we did for truss analysis and convert so that we get an answer in inches. Now, just to make sure that you at least break out your Casio FX 115 ES Plus or similar scientific calculator at least once in this class, what do we get when we check this out? And I'll give you a hint, it's a small number. It's positive, by the way. Anybody have an answer for me? 0.01. There we go. So therefore, delta axial is 0.01 inches downward. So what does this mean? What do these two numbers mean? Okay, here's what they mean. If I consider only flexure, then the deflection is 3.36 inches. If I consider flexure plus axial, then the deflection's what? 3.37. Exactly. So did doing all that extra work for the axial deflection really matter all that much? No. And to be clear, in most frame analyses, that will always be the case. Now, what we're doing here, though, I do want to make one point. Whenever you're running a software analysis, it will usually compute both by default, okay? So if you're running an analysis and you're trying to check it by hand and you're getting this and the program's getting that, like theoretically, if the structure's determinate and you're handling rounding and everything, you should get the exact same answer. So if you're getting something different, this might be why. Okay, if you're only considering flexural deformations, your deflection might be a little bit different. Okay, everybody with me so far? Okay, does anybody have any questions on the example? Hopefully this is pretty rote at this point. Okay. All right, I do want to talk a little bit about shear deformations, and then we're going to call it for today. I want to be clear, I'm not going to make you all do any shear deformation problems, but this is more of a food for thought for later on in your structural engineering careers. Okay? So just to make sure that we're clear what we're talking about with shear deformations, so if I have some beam, some element, a flexural deformation is a mode that looks something like this. You're actually taking the element and bending it, okay? A shear deformation would be if the element is actually undergoing like a shear. So in other words, what we're trying to do when we consider shear deformations is actually consider like this effect on the element. It actually undergoing this change in angle, okay? Now, if you wanted to incorporate shear deformations, what you would do is you just add another term, okay? And the format of that term is pretty straightforward. So if we have a little m big M over EI or a little f big F over EA, in order to account for shear deformations, we just have a little v big V over GA. Now, the integral so whenever you do the derivation, there's like a little bit of extra stuff left over related to the beam's geometry. And so we throw that in a little term we call K. Okay? So the fortunate thing is K's are lookups. So what do you need? You need a real shear function. You need a virtual shear function. You derive them the same way. Okay? Real structure, virtual structure. In the virtual structure, just remove all the loads and place a single load on the structure with a magnitude of 1 at the point of interest in the assumed direction. Okay? The G value, that's the shear modulus. Do you all remember that from Engineering 216? So materials have an elastic modulus, a Young's modulus, but they also have a shear modulus. You can relate that with Poisson's ratio. Remember Poisson's ratio? When you take something, you stretch it, it also gets thinner. Bring all that stuff back. We need the cross-sectional area of the member, but then there's this term K. Again, K is just, basically it's just these leftover terms from the integral that's related to the beam's geometry, but the nice thing is that you can derive those. So like if you have a beam that looks like a rectangle, then K ends up being exactly like 1.2. If you have a circular beam, then K is 10/9. If you have an I shape, K is close enough to 1 that you can just go ahead and just use 1. And whenever you're using an I-shaped beam, the area is just the area of the web, the middle part. Remember, flanges and web. Okay. Now, one of the things I want to mention is when should you consider shear deformations? Like when, as the analyst, do you even care? Okay. Shear deformations start to matter when the beams get deep. Okay. When you have really, really deep beams. And what I mean by deep is I'm talking about an element that is deep when compared to how long it is. Okay? So there's a couple real world examples that I would mention. One of them is what's called a transfer beam. So a transfer beam would be something like this. So like, have you ever been, for example, in a really large hotel where the lobby extends over a couple different stories, right? And then the rooms are on top of that. You have this really large open lobby. Well, there's going to probably be some really, really heavy beams that are holding up the rest of the building up here. And so these elements, we call those transfer beams or transfer girders, those suckers are really big, okay, because they're kind of holding up the rest of the building. So they're really deep as a function of their, when compared to their length, okay. So this would be an element where you would probably want to consider shear deformations. Another element would be something like this. So this would be a hammerhead pier and a bridge support, okay. And this element, if you treated this like a cantilever beam, it's not very long, but it's really deep because there's really large concentrated forces right here. So the beam has to be pretty big in order to handle that. Another consideration where you might want to consider shear deformations is a shear wall. So in between columns and beams, we actually put a solid wall there in order to keep the building upright when subjected to lateral loads. So those would be situations where shear deformations would matter. Okay, and to kind of walk you through it, okay, I want to give you an example, and don't worry, you won't need to do any math on this. But I have a beam here. It's 25 foot long. It's got 3 kips per foot on it. Okay, I have here a beam, and we're going to say it's made out of steel. Okay, so for structural steel, the Young's modulus is 29,000 ksi, and the shear modulus is about 11,000 ksi. Those are sort of lookup terms. Okay. And so what I'm going to do is I'm going to show you what happens when you start using different rolled shapes, and I'll show you what the answers come out to be. So again, what we're going to do is we're going to look at, so for this, all we're looking at is the flexural deformation and then the shear deformation term. Remember, the K value is going to be 1 because we're going to use I shapes. Now, what we'll need is we'll need real moment functions and we'll need virtual moment functions, but we'll also need real shear functions and virtual shear functions. And I went ahead and derived those down here. So if you want, you could follow along with this. This could be something you could do on your own. So I've got real and virtual, real and virtual. And what I'll do is integrate from here to here and just double it to get the answer. So let's start off considering a W14 by 26. Have you all, I think we talked about this in the analysis project video, but just to recap, y'all remember what these two numbers mean, the 14 and the 26? What does the 14 mean? It's generally about how deep the beam is in general. You're about right. Now 14 is about how deep it is. What about the 26? That's how heavy it is, right? So a W14 by 26 is about 14 inches deep and it weighs 26 pounds per foot. Okay? So I have a 25-foot long beam, and the beam is about 14 inches deep. So I went ahead and computed its L over D ratio. So it's about 20.6. This is a somewhat slender element. This is the area of the web. This is the moment of inertia, because we need the moment of inertia here, we need the area here, okay? Now, what happens if I go through and I chug out the deformations, okay, I get that the flexural deformation is about 3.7 inches, and the shear deformation is about 0.071. So if I divide the two, this is only about 1.9% of that. So in a problem like this, you could probably just ignore the shear deformations. You don't really need to consider it, okay? But what happens if I keep everything the same, but I use a deeper beam? So what happens if I use, let's say, a W24 by 76? So this is a bigger element, okay? So it's got a bigger area, a bigger moment of inertia. It's just a stronger, stiffer element, okay? But it's also got a smaller L over D ratio. Now, what's going to happen to the flexural deformation and the shear deformation? They're both going to get smaller. They're going to get smaller because the element's getting bigger, right? And they both do. So here's what happens. This gets smaller and this gets smaller. Well, watch what happens when you compare these two. If you take this divided by that, now it's about 5.5%. So now you're starting to see what happens with the error if you start to ignore this, okay? And if the element gets even deeper, and now we're getting past an L over D ratio of 10, which, you know, a rule of thumb is if your L over D ratio is 10 or smaller, you really need to start considering shear deformations. What happens? The deflections get smaller, but when you compare the two, now you're like over 10% error. You're that much wrong, okay? So my advice would be, if you ever have an L over D ratio of 10 or smaller, you need to consider this, or your answer is going to be wrong. Most software analysis packages actually can account for shear deformation, and usually what happens is there's just a little button that you just check on or off. And this is another one of those things where if you were to do this analysis by hand, the computer will probably give you the sum of these, whereas you might just compute this. So this will be one of those areas where your answer will deviate from what the software gives you. It's not that the software is doing anything wrong, it's just considering this integral, and you might not be, okay? Does that make sense? Okay. All right. Let me stop for a sec, see if anybody has any questions. That is the end of coverage for exam 2. That's what I expect you to know. You have a homework that is due Wednesday. And again, I'm not accepting late homework on that assignment because I'm going to give you the solution right after it's due. But it's a relatively short problem. So make sure you get that done. Get your MassCAN software installed by Wednesday. We're not going to use the software on Wednesday. We're not going to use it on Friday for the exam. But when we come back next week on Monday, I want everybody to bring your laptops because we are going to do MassCAN analyses together in class. That's all I have, everybody. I will see you all on Wednesday.